Hi guys, welcome back to the channel. In this video we are going to discuss about flip-flop conversions from D to SR, JK, T. So let's get started. So in the previous video we have discussed the already flip-flop conversions, these two, from JK to remaining 3, from SR to remaining 3. So in this video we are going to discuss from D flip-flop to remaining 3. So if you have missed these two concepts or these two videos, I am giving these two videos in the description box. Please check it out first because those are the basic things. So in this video we are going to just focus on D flip-flop to SR flip-flop, D flip-flop to JK flip-flop, D flip-flop to T flip-flop conversions. So let's see how to do that. So before seeing the conversion from D flip-flop to the SR flip-flop, so this flowchart is very important for the conversion. These are the points that we need to keep in mind for the conversion. These things we have discussed in the previous two videos, but just lightly we are going to discuss here also. If you observe the first point, draw the truth table of the remaining 3 flip-flops, means other than D flip-flop, that is SR, JK, T flip-flops, we are going to have the truth tables. So the next step is draw the excitation table of the D flip-flop, that is the main thing in this case, means in this video. So use the K-map and K-map or general Boolean algebra to minimize the expression of D and finally draw the logic circuit. So let's see how to do that with the help of conversion. The first conversion is from, let's see that. So the first conversion is from D flip-flop to the SR flip-flop. So in this we have the SR flip-flop because we are building the SR flip-flop. So that is the reason we are going to have the SR flip-flop truth table. So with the column left of D. So I have completed the first step, that is draw the truth table of the required flip-flop. So the required flip-flop is yes. So I draw the truth table of the SR flip-flop. So I hope you know how to build the truth table of the SR flip-flop. So I have made separate videos on separate flip-flops, SR flip-flop, JK flip-flop. I am giving the videos in the description box. So if you know, just get forward. So for the filling of the D row, means D column, we are going to have the excitation table of the D flip-flop. So that is the thing that I am saying about. We need to compare Qn and Qn plus 1 like this as you are seeing there. The present state is known as Qn and the next state is known as Qn plus 1. You can also see with the help of the arrows that I am indicating how it is changing. But if you observe last two cases, especially in the as this is the SR flip-flop, the last two cases would be don't care conditions. The present state would be converted as zeros or ones that we don't know. That is why we took as don't cares. So for this we are going to have the excitation table of D flip-flop. So this is the excitation table of the D flip-flop. So Qn plus 1, D. So basically what is meant by excitation table? The output, then the corresponding output, which input would be there. So simply saying, so if present state is changing to the next state, then for that situation what will be our output? So if you see example I am saying, if you see the first one, so 0 is changing to 0, next state also 0, present state also 0. So in that case what is D? That is 0 only. So we already know basic of D flip-flop. What is meant by D flip-flop? The input D would be equal to the Qn plus 1. So you have observed there. So the Qn plus 1 that is highlighted in blue, the green color that is highlighted in D. So that is D column and Qn plus column are same. So this is the basic property of the D flip-flop. So here excitation means whatever may be the Qn, it will changing to the Qn plus 1, that same as D. With the help of this we are going to fill the SR flip-flop truth table. So if you missed what is the full excitation table or I need to learn more about the D flip-flop, you can watch this video that I am giving there. So this is also in the description box. So let's start filling the SR flip-flop truth table. So we have left one column that is D. You are going to check the excitation table of D flip-flop and this truth table, and we are going to fill all these things. So in this case for the D flip-flop to SR flip-flop, just we need to have the excitation table of D flip-flop, that's it. So if you compare 0 is changing to 0 in excitation table, that is output is or the input D, so that is 0. So fill that as same as that in the truth table of SR flip-flop, 0. Similarly, if you observe the next case, the present state is 1 and the next state is also Qn plus 1, that is 1 in the SR flip-flop truth table. If you observe the same thing in the excitation table of D flip-flop, so that the same transition, the Qn plus 1 to means the present state to next state is 1 to 1 is, if you observe corresponding D is 1. So fill directly in the truth table of SR flip-flop 1. So I hope you can fill the remaining things by seeing the excitation table of the D flip-flop, but you need to start where that 1 1 changes to 1 1, the present state is changing to next state as 1 1. Because the last two cases we don't know what is the next output, so we are taking directly D as don't care situations for the SR flip-flop. You can see over there. So this is our final thing, that of D column. is filled with the help of the excitation table. So use the K-map for finding the Boolean expression of the existing flip-flop. Means you need to find the expression for D using the column of D by simple Boolean algebra, or you can use the algebra means the SOP or POS formats where there is minterms. You have to have the corresponding minterms. So likewise you have to take, or you can use the K-map for the minimization. So in this case I am going to use the K-map for the minimization. So this is the K-map that you can see over there. So D, that is sigma 145. So we have minterms or ones in the positions of 145, and we have don't care situations in the 5 and 6 position. So according to that, as we have three variables only, that is S, R and Qn, so we should not consider the next state output, that is the main output. So we have only three inputs, so I took the three variable K-map. So fill all these things and you can see it like that. So you can group like a green group and a blue group, that is 1 5 in the blue group, and the largest group of 4 elements over there. So the S group, that is largest group, is the S, we can simply say. So the blue group is corresponding to R bar Qn. So we have obtained the output expression D. So we are going to have the block diagram as well. So this is the block diagram of D flip flop to the SR flip flop, or we can say this is the D flip flop. So we are passing input as S plus R bar Qn. So this S bar means S plus Q R bar Qn can be left like this also, or we can also expand this. So now we will see that block diagram after expanding this one. So this is the final diagram of the SR flip flop, I can say. So you can also observe that. So we have only D flip flop. So with the help of some logic gates I have built, or I am passing S and R. So the whole logic it becomes as SR flip flop. So finally from the OR gate you can also observe that we are getting S plus R bar Qn. So I am passing into directly D. So this is equivalent to the SR flip flop because we are building the SR flip flop. So with some logic that we have used the D flip flop, and we have made some logic gates and like these connections, and we have made inputs as SR. So this whole logic or this thing that is equivalent to the SR flip flop. The next conversion is the D flip flop to the JK flip flop. So if you see here, the first step is to draw the truth table of the JK flip flop. So for the JK flip flop, I hope you know the same, because JK flip flop and SR flip flop are almost same, but a small change. If you pass as JK or SR in the positions, if you pass in the position of SR, that is 1 1, the final output would be forbidden state or don't care condition. But in this case we are going to have the toggle state. So if you observe clearly from Qn to Qn plus 1, when JK are both 1 1s, what is this changing? If you see the last but one in the truth table, that is 0 is changing to 1. From Qn to Qn plus 1 I am saying. So 1 is changing to 0, the last case. So this is known as toggle condition. So I hope you know the truth table of the JK flip flop. Remaining all three conditions are same. So in this also I have left a column, that is D column. Again we are going to fill this D column with the help of the excitation table of the D flip flop. So in the same fashion, if you observe the JK flip flop truth table also, so we have transition from Qn to Qn plus 1 as 0 0 for the first situation. So the same situation we are going to compare in the excitation table of the D flip flop, and again we are going to have the same thing, the same input D in the truth table also. So if you have compare the excitation table, 0 is changing to 0 as the D input as 0, so fill them directly. So the remaining all things I hope you can fill this, because the same thing, the same situation that we have saw in the SR flip flop also. So it is nothing just but by seeing the excitation table from Qn to Qn plus 1, what is D? So in the same fashion, if you compare the Qn to Qn plus 1, so that D is corresponding with the help of the excitation table, we are going to fill this D means as JK flip flop. I hope you can understand. So in this we don't have the don't care situations, so we are going to follow up to the last one. The last one is from transition 1 to 0. So you can also observe in the excitation table, that is 1 0 as corresponding 0. So put 0 directly in the JK flip flop truth table. So as usual, the same thing, using K-map we are going to find the Boolean expression of D, and we are, that is D flip flop, and we are going to again convert to that as JK flip flop. So this is the K-map that you can also observe here. So as we have three variables here, that is J, K, Qn. So Qn plus 1 is our final output, that is main output. So you should not consider the Qn plus 1. So as we have three variables, I took three variable K-map. So in the row wise I took J, in the column wise I took K, Qn. So if you observe, that is we have min terms in the position 1 4 5 6. So just feel we have two groups over there, that is 1 5 as blue group and 4 6 as our green group. You can, that is corner grouping. So for the two groups we have two output expressions, that is d is equals to j dot qn bar plus k bar dot qn. Again the same thing that we are going to follow, as we obtain the output expression that d is equals to something. So as we are having the d is equals to something, again we are going to follow the input, the equation that we got, we are going to pass in the d flip flop as it is the same thing. So we can leave like this is the jk flip flop, or we can implement, or we can expand this with the help of the expanded diagram. So let's see that also. This is the expanded circuit diagram that you can see over there. So the final output, that is j dot qn bar, that is one product term, k bar dot qn, that is one product term. So as we have two product terms, we have two AND gates, so we have k bar, so for that I took a NOT gate. So simply we are also having qn bar and qn. So simply we are going to have the outputs also from the as feedbacks. So we have two inputs jk. So I hope you can build the circuit diagram from the output expression. From this we can say this whole circuit diagram is equivalent to the jk flip flop. So whatever may be the circuit diagram present inside that, but the logic, the same logic that we are going to obtain from this. And we can say we are implemented the d flip, with the help of d flip flop, jk flip flop is implemented. The last and final conversion in this is the d flip flop to the t flip flop. So if you observe, this is the t flip flop truth table. So I have left again the same column, d column here. So I hope you know what is meant by d means t flip flop. T means here toggle. So when t is equals to 0, qn plus 1 would not be changed from qn to qn plus 1. When t is equals to 1 only, the t means that t is equals to 1 only, qn will change or toggle to the qn plus 1. So if you observe, when t is equals to 1 for the two cases, last two cases, qn is 0 and 1. Then qn plus 1 is 1 0, that is toggling. But if you see for the first two cases, that is the same as t is. qn and qn plus 1 are same. So when t is equals to 0. Again the same thing, we are going to compare qn and qn plus 1 from the excitation table of the d flip flop, and again you are going to fill in this t flip flop truth table. Likewise, you are going to fill all the truth table, t flip flop truth table, using the excitation table of the d flip flop. So I hope you know the comparison is very easy. So last case is from 1 0, corresponding d is 0. If you also observe in the excitation table of d flip flop, that is the same. So qn is changing to qn plus 1 as 1 to 0. So corresponding d is 0. So using k map, again we are going to find the output expression or the expression of d, and for that d we are going to have the things, the circuit diagram. Sorry guys, that I forgot to mention is that, is this we have two variables here? Yes, we have only two variables here. So then we are going to use the two variable k map. So instead of using two variable k map, we can just simply using Boolean algebra or SOP formats, we can have the product term, because only two variables, right? So if you observe the output expression of d, we have only two means min terms here, that is in the one position, two min term to second position. So in the one position min term m1, that you can also observe that. So t qn, that is t means here for the first means m1, that is first min term, if you observe, that is t bar qn, just normal SOP formats. So if you observe the next one, that is t dot qn bar. If you add both of them, that gives our d expression. So simply it is like from means the format called XOR operation. So that is t dot qn bar and t bar qn, it is somewhat like XOR format. So simply take d is equals to t XOR qn. And finally we have the diagram here that you can also observe here. Both the flip flops are t flip flops. In the first one, that is our builded circuit with the help of the d flip flop. But with the help of only single XOR gate, we can convert this whole d flip flop to t flip flop. So the term is t XOR q. So simply have the XOR gate, and q is taken feedback. So simply this is the implementation, and both the flip flops are same, that is t flip flops. I hope you understood this video. In the upcoming video, we are going to see from t flip flop to the remaining three flip flops. So thanks for watching up to now.